inside the most dangerous objects in the universe. Picture this. You're standing at the edge of the cosmos, staring at an object so impossibly dense that a single teaspoon of its material would weigh more than 1 billion tons. Now imagine something even more terrifying, an abyss so deep that not even light can climb back out. These aren't science fiction nightmares. They're real. They're out there right now, and they represent the most extreme conditions physics allows to exist in our universe. I'm talking about strange stars and black holes, the universe's ultimate predators. Today, we're diving into the cosmic danger zone to understand what makes these objects so deadly, how they form, and why they might be more important to our existence than you ever imagined. Let's start with something that sounds impossible but is absolutely real: neutron stars. When massive stars, at least 8 times the mass of our sun, exhaust their nuclear fuel, they don't fade away peacefully. Instead, they explode in spectacular supernovae, briefly outshining entire galaxies. But here's where it gets wild. Sometimes after the explosion clears, the core doesn't disappear. It collapses. And I mean really collapses. Imagine crushing the entire mass of the sun into a sphere about the size of a city, roughly 20 kilometers across. That's a neutron star. The gravity becomes so intense during the collapse that protons and electrons get squeezed together, forming neutrons. It's like the universe took a star and compressed it into the densest ball of matter possible, without creating a black hole. The numbers are genuinely mind-bending. A sugar cube-sized chunk of neutron star material would weigh about 100 million tons on Earth. That's roughly the weight of Mount Everest compressed into something you could hold in your palm if your hand didn't instantly vaporize from the radiation and heat. These objects spin incredibly fast, some completing hundreds of rotations per second, and they generate magnetic fields trillions of times stronger than anything we can create on Earth. But neutron stars are just the opening act. What if I told you there might be something even stranger lurking in the cosmos? Enter strange stars, one of the most fascinating hypothetical objects in theoretical physics. To understand them, we need to talk about what's inside neutrons themselves. Neutrons aren't fundamental particles. They're made of smaller components called quarks, specifically 2 down quarks and 1 up quark. Under normal conditions, quarks are confined inside protons and neutrons. They never exist freely in nature. But normal conditions don't apply inside neutron stars. The pressure at the core of a neutron star is so extreme that something bizarre might happen. Physicists have theorized that under these conditions, the quarks might break free from their neutron prisons and rearrange themselves into a different configuration involving strange quarks, creating what's called strange matter. Here's the truly unsettling part. Strange matter might be more stable than normal matter. If this theory is correct, a neutron star could undergo a phase transition, converting from ordinary neutrons into strange matter from the inside out. The result would be a strange star, an object even denser than a neutron star, potentially glowing with a faint light from thermal radiation and strange quark interactions at its surface. Now, before we go further, I need to emphasize something important. Strange stars remain theoretical. We have no confirmed observations of them yet. The physics is solid enough to take seriously, mathematically consistent with what we know about quantum chromodynamics, but we haven't found one in nature. That said, some observations of unusually small, dense, compact objects have made astronomers wonder if we might be looking at strange stars without realizing it. What would happen if you encountered strange matter? Some versions of the theory suggest that if strange matter touched ordinary matter, it could convert it into more strange matter in a chain reaction. Imagine a cosmic infection that could theoretically convert entire planets or stars. It sounds like science fiction, but it's a legitimate topic of research in theoretical physics. If you're finding this fascinating, drop a comment below. Are strange stars real, or are they just mathematical curiosities? Let me know what you think. Now, let's talk about the heavyweight champion of cosmic danger: black holes. If strange stars are hypothetically terrifying, black holes are demonstrably, observationally, undeniably the most extreme objects we know exist. A black hole forms when so much mass gets compressed into such a small space that space-time itself curves infinitely inward. Einstein's general relativity, one of the most successful theories in physics, predicted them mathematically in 1915, though Einstein himself doubted they could exist in nature. We now know they absolutely do. The defining feature of a black hole is its event horizon, the boundary beyond which nothing, not matter, not light, not information itself, can escape. It's not a physical surface you could touch. It's more like a point of no return in space-time itself. Cross that boundary, and the laws of physics as we understand them say you're never coming back. Black holes come in different sizes. Stellar mass black holes form from collapsed massive stars, typically ranging from about 3 to several dozen times the mass of the Sun. Then there are supermassive black holes, monsters containing millions to billions of solar masses, lurking at the centers of most large galaxies, including our own Milky Way. For decades, black holes existed primarily in mathematical equations and theoretical papers, but we've now observed them directly and indirectly in multiple ways. In 2015, the LIGO experiment detected gravitational waves, ripples in space-time itself, produced by two black holes spiraling into each other and merging. This discovery confirmed a major prediction of Einstein's theory and opened an entirely new window for observing the universe. We've also watched stars orbiting the supermassive black hole at the center of our galaxy, called Sagittarius A star. By tracking these stars over decades, astronomers calculated that they're orbiting an invisible object containing about 4 million solar masses packed into a region smaller than Mercury's orbit. There's no other explanation that fits the observations. Then in 2019, the Event Horizon Telescope, a planet-sized network of radio telescopes, captured the first direct image of a black hole's shadow in the galaxy M87, showing the glowing accretion disk of superheated matter swirling around the event horizon. In 2022, they released an image of our own galaxy's supermassive black hole. These aren't artists' concepts. They're actual observations of the universe's most extreme objects. What would happen if you fell into a black hole? The experience would depend on the black hole's size, but for a stellar mass black hole, the answer is genuinely horrifying. Spaghettification. As you approach the event horizon feet first, the gravitational pull on your feet would be significantly stronger than the pull on your head because your feet are closer to the black hole's center. This difference in gravitational force, called a tidal force, would stretch you vertically while compressing you horizontally. The effect increases dramatically as you get closer. Long before you reach the event horizon, you'd be stretched into a thin stream of atoms. It wouldn't be quick. You'd remain conscious for at least part of this process, experiencing the most extreme form of death physics allows. Your individual atoms would eventually cross the event horizon and fall toward the singularity, the infinitely dense point at the black hole's center, where our current laws of physics break down completely. Here's something even stranger. Due to time dilation, an outside observer watching you fall would see you slow down as you approach the event horizon, appearing to freeze just at the boundary, gradually redshifting out of visibility. From your perspective, you'd cross the horizon in finite time, but to everyone else in the universe, you'd appear to take forever to fall in. Time itself becomes warped near these objects. Before we continue, let me ask you this. Would you rather fall into a black hole or encounter strange matter? It's a terrifying choice, but let me know in the comments which cosmic death you prefer, hypothetically speaking, of course. Now let's address a common misconception. You've probably heard black holes described as cosmic vacuum cleaners, voraciously sucking up everything around them. This idea appears in countless movies and shows, but it's not quite accurate. Black holes don't magically pull harder than any other object of the same mass. If our sun suddenly became a black hole of the same mass, which it won't because the sun isn't massive enough, Earth's orbit wouldn't change. We'd keep orbiting at the same distance, experiencing the same gravitational pull. We'd freeze in the darkness without the sun's heat, but we wouldn't get sucked in. The danger comes from getting close. If you're far enough away from a black hole, you can orbit it safely just like you'd orbit a star. Many star systems likely contain black holes with companion stars orbiting them normally. The accretion disks we observe around black holes form from material that gets too close within a certain distance where stable orbits become impossible. So black holes are dangerous, incredibly so if you're nearby. But they're not roaming the galaxy, hoovering up everything in sight. They follow the same gravitational rules as everything else. They're just much more compact, which allows you to get much closer to their mass before reaching a point of no return. Why should you care about these cosmic monsters? Because they're not just dangerous curiosities. They appear to play a crucial role in how galaxies evolve and how the universe developed its current structure. Nearly every large galaxy we've observed contains a supermassive black hole at its center. Our Milky Way has one, as we discussed. The galaxy M87, where we imaged that first black hole, has one containing about 6.5 billion solar masses. These aren't coincidences. There appears to be a fundamental relationship between a galaxy's mass and its central black hole's mass. When matter falls into a supermassive black hole, it doesn't just disappear quietly. The material in the accretion disk gets superheated to millions of degrees, radiating enormous amounts of energy across the electromagnetic spectrum. Some of this energy gets channeled into massive jets that blast out from the black hole's poles at nearly the speed of light, extending for hundreds of thousands of light years. This process provides feedback that regulates star formation throughout the galaxy. When the black hole is actively feeding, the energy it releases can heat gas clouds and blow them out of the galaxy, preventing them from cooling and collapsing to form new stars. When the black hole is dormant, gas can cool and star formation resumes. The cycle appears to control how galaxies grow and evolve over cosmic time. Remember our episode on deep field images, where we looked at thousands of galaxies in a tiny patch of sky? Many of those distant galaxies likely contain actively feeding supermassive black holes in their cores, helping shape their structure and evolution. The most massive black holes in the early universe may have influenced the formation of the first galaxies after the Big Bang. So these dangerous objects aren't just cosmic hazards to avoid. They're fundamental components of cosmic evolution, artists sculpting the large-scale structure of the universe. Let's bring this full circle. We started with neutron stars, the collapsed cores of dead massive stars, packing the mass of the sun into a city-sized sphere. We explored the possibility of strange stars, hypothetical objects where quarks break free and matter reorganizes into an even more exotic state. Then we confronted black holes, regions where gravity becomes so intense that space-time curves infinitely inward, creating a boundary that nothing can cross back over. These objects represent the absolute limits of what physics allows. They show us what happens when we push matter and energy to their breaking points. They're laboratories for testing general relativity in its most extreme regime, and they're real features of our universe, not mathematical abstractions. The universe contains wonders and terrors in equal measure. Strange stars might not exist, or they might be hiding in plain sight among cataloged neutron stars. Black holes definitely exist, and they're simultaneously the universe's most destructive forces and essential engines of galaxy evolution. They destroy individual stars and planets that venture too close, but they also regulate the birth of new stars across entire galaxies. If this journey into the cosmic danger zone left you wanting more, make sure you're subscribed so you don't miss future episodes. We've got more extreme physics, more cosmic mysteries, and more mind-bending concepts coming your way. Hit that like button if you enjoyed this deep dive into the universe's most dangerous objects. And here's a question to leave you with. If you could safely observe one of these objects up close, protected from its dangers, which would you choose? A neutron star with its crushing gravity and intense magnetic fields? A hypothetical strange star glowing with exotic matter? Or a black hole with its warped space-time and swirling accretion disk? Let me know in the comments. The universe is more extreme, more dangerous, and more fascinating than we often imagine. These objects exist out there right now, continuing their cosmic dance, shaping the structure of space and time itself. And we're just beginning to understand them. Thanks for watching, and I'll see you in the next episode where we'll explore even more cosmic mysteries.